Hi folks, welcome to our last lesson on acids and bases. This one is going to be pretty calculation heavy. These three sections that we're going to deal with, yeah, lots of calculations. Hopefully we're understanding the theory from everything we've done before this, and we can handle these calculations. Now we go back a little bit in time to understanding our ice charts, as well as using our titrations like we did in the previous chapter. We've also dealt with those in Chem 11 as well. I've posted a few videos on titrations for you on Schoology because those are very important when it comes to going into chemistry at university. If you're not going to take chemistry at university, then feel free just to follow the calculations portions, just to understand what those calculations look like. And I'm going to go over a few of those here as well. Okay. The notes I think on this section should be fairly straightforward. These Ka, Kb calculations that we're dealing with are only going to be in the weak acid, weak base section, and usually we're dealing with mostly strong acids and strong bases in the titration portion, however, not always. But I'll get to those when we talk about that. Okay. And there's also this assumption that we're making to avoid the quadratic equation. So this is known as the 5% rule. And essentially, if the concentration of our acid is 1,000 times larger than our Ka value, which is most of the time, then we are going to make that assumption that whatever our concentration is, in this case this X, we're going to state this that 0.0 minus X is approximately 0.60. Okay, so we want to either state that it's approximately 0. Obviously, the numbers will change based on the question you're dealing with, or we'll say based on 5% rule. Okay, so one of those two statements needs to be made in your calculations on your test, just so that we know that you're making that assumption. All right, that being said, I've got 2 Ka examples, 3 Kb examples, and 3 titration examples. Let's get into it. Okay, first example we're dealing with here is trying to find the pH of a 0.5 molar solution of hydrofluoric acid, and it has a Ka of 3.5 times 10 to the negative 4. Okay, so first up, we need to do HF plus H2O is in equilibrium with F minus and the H3O plus. Okay, and now I titled this section as the return of the ice charts. So we're going to start with this ice chart, and then we'll get back into our calculations here in a moment. So what are we starting with? Well, remember, we ignore water because it is a pure liquid. Okay, so we're going to have this 0.50 for our HF. And since we're starting with that, that means that we have no information about the H3O plus or the F minus. So we're going to leave those there. Now we've got a lovely 1-to-1 ratio, so when we're looking at our change, the change we see here is going to be the same as the change here. So let's take a look at this. We are going to be going from this HF to the F minus in here, so we're going to gain this plus X on those sides, which means we have a minus X on this side. So when we're looking to find our equilibrium here, at equilibrium, our F minus is a concentration of X, our H3O plus is a concentration of X, and we have a 0.50 minus X for our HF. All right, now I said we're going to use that as a 5% rule if our concentration is more than 10 times, or sorry, more than 1,000 times this, and it is, so we are going to write down that we assume 0.50 minus X is approximately 0.50. Okay, now we have enough information that we can start to write this out, our Ka expression, and then solve for our value of X. So just to have a little bit more space on here, I'm going to rewrite this point that at equilibrium, we have a concentration of 0.5, concentration of X, and a concentration of X. So our Ka expression is the concentration of our products multiplied by each other, raised to the powers of their coefficient. Everything here is 1, so that makes that part easy. And divided by the concentration of our reactants. And again, we ignore our pure liquid, in this case, water. So here is our Ka expression. If we plug in our values that we have, well, our concentration of F minus and concentration of H3O plus is these X. So we end up with an X squared divided by our concentration of HF, which is this 0.5. And we were given our Ka value of 3.5 times 10 to the negative 4. Okay, so I'm going to bring this multiply over, and we are going to say X is equal to the square root of 0.5 times 3.5 times 10 to the negative 4. Right, multiply both sides, and then to get rid of the squared, I square root this. And this gives me my X value of 0.0132 molar. Okay. Now, we said X is also our H3O plus, right? So that is our H3O plus concentration. Okay. But that wasn't our goal for this problem. Our goal was to find the pH. Well, we know that pH is the negative log of that H3O plus concentration. So when I plug into my calculator the negative log of this 0.0132 molar situation, I get a pH of 1.88. Okay, so hopefully that one makes sense. If you need any clarifications, please post those in the questions. All right, moving on to question 2. What concentration of benzoic acid gives a pH of 3.30? Okay, so here's our benzoic acid, C6H5COOH. Okay, now in order to get this pH value, what we're looking at here is we need to know the concentration of H3O plus equals 10 to the negative pH. So when I plug in this value into this equation here, I end up with a 0.000501 molar. Okay, so 5.01 times 10 to the negative 4. We also need to take a look at our ice chart once again. And so in order to do that, we have our C6H5COOH plus water is in equilibrium with those two situations. Okay. We are looking at our initial, our change, and our equilibrium values here. And again, we ignore the pure liquid. So we are introducing some of this benzoic acid into a solution. We don't know how much. Okay, so that's the X value. We're trying to find this. And since we're putting this into water, we are starting off with 0 on both of those. Okay. Well, to get this pH, we have this concentration of H3O plus, so that means we are adding this 5.01 times 10 to the negative 4 for both of these situations because they are a 1-to-1 ratio. So if we use that pH to get our H3O plus concentration, that's also the same value for our C6H5COO minus. Okay, now if we're adding those, that means we are subtracting that value from over here. And so in equilibrium, our concentration of the acid is the x minus 5.01 times 10 to the negative 4. Okay, and then over here, they are that concentration that we determined, 5.01 times 10 to the negative 4. Okay, we are going to use these equilibrium values to figure out our Ka expression. Okay, so we have our Ka is the concentration of our reactant, or sorry, our products. So our benzoic ion and our H3O plus, our hydronium ion, divided by the concentration of the benzoic acid. Okay, we know these two values from the ice chart, and we know this bottom value from the ice chart. Now, because we aren't sure what this concentration is, we are going to not make an assumption. Okay, but I'll show you how that works out here in a second. Now, we need this Ka value, so we want to take a look at the back of the textbook at our data sheets, and I have a value of 6.5 times 10 to the negative 5. Okay. Now, if we go back, these two we had said from our ice chart, those are the same value. Okay, so I'm going to have 5.01 times 10 to the negative 4 squared, right? Because both of them had that value and we're multiplying those. And instead of this unknown here, we have x minus 5.01 times 10 to the negative 4 as my denominator. Okay. I'm not going to show all the steps here, okay? But we've got numbers squared. And if I switch those two places, right? So I'm going to multiply both sides by this value to move it over here, and I can then divide both sides by this value to move it over here. Okay? So when I do that step, I get my x minus 5.01 times 10 to the negative 4 over there. And I have my 6.5 times 10 to the negative 5 over here. So on my left-hand side, I get this 5.01 times 10 to the negative 4 squared, and then that number divided by my 6.5 times 10 to the negative 5. 0.00386.2. Oops. Just like that. So 003862 equals x minus 5.01 times 10 to the negative 4. I'm going to add this value to both sides, and I get x is equal to 0.0044 molar. Okay, and just remembering I had 2 decimal places in my pH. I need 2 decimal places, or 2 sig figs in my final answer. Okay, so our concentration of benzoic acid that will give us a pH of 3.3 is 0.0044 molar. Okay, those are our 2 examples of Ka type problems. We're going to move on to Kb problems, which, as I said in the notes, are very similar, just that we're dealing with Kb and OH minus instead of the Ka and the H3O plus. So just an extra step to get things started.